Today we'll be doing 2004 mechanics problem number 1. As I said before, it's suggested that you have the problem sort of next to you so that you're able to see the problem as I go through each part, because I'm not going to talk about the problem, I'm just going to solve it. So, starting with part A. Part A asks about the speed of the person just before the collision with the object. So this is merely a conservation of energy problem. They just want to see what the velocity of the person is going to be right before he hits that rock, or that M2. So the way we're going to solve that is how you would solve any conservation of energy problem. You would set your initial sort of potential energy to your final kinetic energy. So your initial potential energy to your final kinetic energy. And we know that his initial potential energy, in respect to M2, he was an L distance away. So as they show in the diagram, there's like a distance L away from point C, and this is where the person is, and then this is where the rock is. And then they also say that this is also a distant L. So if, with respect to the rock, he is a height L away. So his initial potential energy is therefore mgl, and his final kinetic energy is the same formula, 1/2 mv final squared. So now we just solve for v final. The m's cancel out. Bring the 2 up here. So we get 2gl is equal to vf squared, or our final answer is vf is equal to square root 2gl. Alright, so that's it for part A. Part B. Part B asks for the tension on the rope just before the collision with the object. So now we're looking to see with what force is this rope having on that person. And you can sort of think of it as like a person swinging on like a rope like Tarzan. He's like going from here to here. The tension on the rope is equal to this sort of radius. And whenever there's a radius, you know that there's going to be centripetal force. So the force on the rope, or on this, is some Fc. So the force acting here is some Fc. So we know that there's centripetal force involved. However, you have to take into account that there's also the weight of the man, his mg. So we have to say that his net force is equal to some centripetal force. So what we're going to say is that Fc is equal to Ft, so the force of tension on the rope, minus mg. Right? So we're saying our net force, the only force acting on the man, is the centripetal force. Right? That's our net force. And it's equal to the force of the tension minus his weight. So Ft minus mg. So now we want to figure out what Fc is. And we know the formula for Fc is Fc is equal to mv squared over r. Now we're going to do some substituting here. As we saw in the last problem, our v is equal to the square root 2gl. So it's going to be m square root 2gl squared and all over r, which is rl. And this simplifies to m 2gl, because it's inside a square root, so square root squared is the same thing, m2gl all over l. M's cancel out, so it's 2mg. That's our centripetal force. So we're saying 2mg is equal to Ft minus mg. So Ft is equal to 2mg plus mg, which is equal to our final answer, 3mg. Okay, so we solved parts A and B. Now on to part C. Part C asks a conservation of momentum problem. They ask, what's the speed of the person and object just after the collision? So they're asking, okay, after this person has collided with the object, What is their total speed together? So now we set up a conservation of momentum problem. So we know that the person had some velocity before he hit the ball or hit the rock, which is what we solved in part A. So we know the person who has mass m had some velocity, but we know that this mass he collides with was stationary. So it has no velocity, it's 0. And then we know that together they move m plus m1 plus m2 with some velocity. So now that they're collided together, they move with some final velocity over here, right? So now what we do is we substitute what we know. As we said in the first one, the final velocity of the person is square root 2gl. So we're going to say m square root 2gl is equal to m1 plus m2 vf. So we say that vf is equal to m1 2gl all over m1 plus m2. And that is our final answer for this part. Okay, and then for our last, the last part of the question, they're asking what is, the second to last part of the question, what is the ratio of the kinetic energy of the person object system before the collision to the kinetic energy after the collision? So how we would do that is, let's find first the kinetic energy of the person before the collision. So we know the kinetic energy of the person before the collision, so this is the person, right? He's falling, gonna hit that rock thing. And we know that the kinetic energy before the collision is just gonna be the kinetic energy of the person because the rock isn't moving. So we're gonna say kinetic energy initial of the person is equal to 1/2 mv squared. We're gonna use that same v from part A, and we're gonna say it's equal to 1/2 m root 2gl squared, which is equal to 1/2 m 2gl. Now, the final kinetic energy is the kinetic energy of this and this together when they're moving together. So it's equal to 1/2 times the total mass, so mass 1 plus mass 2, times that final velocity we solved in part C, this final velocity, which we solved using conservation of momentum. So times this big quantity squared. So this is equal to some algebraic simplifying, m1 plus m2 times m1 squared, so we're squaring every single thing in the parentheses, so m1 squared times 2gl, so this whole thing squared, over m1 plus m2 squared. So we know there's an m1 plus m2 here, m1 plus m2 here, so we can cancel some things out. So we get 1/2 m1 squared 2gl all over, and because there's a square on the bottom, we keep one of them on the bottom, m1 plus m2. Right? So this is our K final. So they want the ratio again of the initial to the final, so we just take, or we divide both things, so initial to final. And our initial, we said, was 1/2, so m times 2gl all over 2. So we're looking at what was here, and we're looking over here now. In retrospect, you could have canceled the 2's ahead of time, but we're just going to do all the canceling later. So we have the kinetic, initial kinetic over the final kinetic. So 1/2 m2g l over 2. And if we divide by a fraction, So we're dividing by k over f. We're simply multiplying by the reciprocal of it. So here I'm just actually going to cancel these because they're useless. So we're going to multiply by this reciprocal. So we're going to put m1 plus m2 on the top, and then m1 squared GL on the bottom. And we see that a lot of things cancel out. This GL cancels with GL. As I said, the 2 cancels with the 2. And then we have an m1 on the top and an m1 on the bottom, m1 squared on the bottom. So there's going to be an m1 on the bottom. So we're going to get our final answer is m1 plus m2 all over m1. And that's the ratio of the kinetic energies. Cool. So now on to the last part, part E, which is asking us the total horizontal displacement from the point A until the person lands in point D. So if you're looking at the diagram right now, point A, point B, and point D. And point C was somewhere up there, but that's irrelevant. So they want this total displacement. That's a bad line. This total displacement x. So we're going to solve for that right now. But first, realize that we know the displacement from A to B, right? We solved it for it previously. Or we didn't solve for it. They gave it to us. It's L. So now all we need to do is figure out what the displacement is from B to D, and we can just add that to L. So to find displacement, we stick with our formula delta x is equal to vxt. And the way that we have to find vx is we have to remember first how to find t, and then second we need to figure out which vx we want to use. But let's find what t is first. So remember our kinematic equation, which is delta x, or delta y in this case. Delta y is equal to vyot plus 1/2 gt squared. And because it's there's no initial y velocity, this goes to 0. So delta y is equal to 1/2 gt squared. So move things around. So 2y over g is equal to t squared. So we know that t is equal to 2y over g. Okay, so now what we're going to do is we're going to see that so they give us this vertical distance b to d, they give it L, and we want to find the time it takes from B to D. So we know that L is going to be the same as our y. So we're going to say that T is equal to 2L over G. So we have T down, so T is okay. So now on to Vx. Vx, we're going to use one of our previous equations that we found. Let me find it. We're going to use, this is the ratio. We're going to use the equation of the final velocity of the person and the mass on the rock together, because we're taking the distance from B to D, and at this point the rock and the person are already together, so we have to take this final velocity, the final velocity here. If we take the final velocity here, it's going to be only the velocity of the person, but we want to take the velocity of both the person and the rock. So we're just going to copy the final velocity we found in that part, and that's equal to m2gl all over m1 plus m2. Okay, so now we have Vx, we have T, we can find delta x, so let's multiply these two together. So m2gl all over m1 plus m2 times 2L over G. Now remember that when you multiply two square roots together, it's the same thing as putting it under one square root. So we're going to put everything under one square root. So we're going to say it's equal to m, and the g's cancel out here because this is all under one square root. So m 4L squared all over m1 plus m2. And this simplifies further to 2ml. Basically, we're just breaking the square root. 2l times m all over m1 plus m2. Oh, remember that this is m1, by the way. I'm sorry. I should keep my subscripts. m1. And then, not forgetting that we have to take into account this distance because they want the full distance from A to D. We simply add L. And that's our answer. Thank you all for listening. That's the end of the problem.